Today we'll be looking at agentic systems like multi-agents. So in the last class, we looked at what agents are, what they do, and all the other capabilities of an agent. Let's do a quick revision of what agents are, then we'll take a look at what multi-agents are. So we looked at this particular point that LLM can only talk, an agent can do, right? LLMs retrieve information, but agents can do tasks, right? An agent is an LLM that's been given hands, right? It does not just tell you how to do something, it actually goes and does it for you, right? It does not gives you just instructions that, hey, you can go in and do this by yourself. Instead, on behalf of you, it can take answers, right? So what is an LLM? Answers your question. What is an agent? Completes your task, right? Let's look at some examples which we already saw in the previous class, which clears the distinction between what an LLM is and what an agent is. So let's say the user prompt is book me a table at 8 p.m. So plain LLM response, what it will do is, sure, you can call the restaurant or use open table to book, right? It will just give you the instructions. But what an agent response will be, actually books the table and replies done, the table is booked for 8 p.m. confirmed, right? So the second example would be, what's the weather tomorrow, right? Let's say if you ask this question, a plain LLM, what plain LLMs without agentic capabilities will do is, I can't check the live weather for you, but you can look at www.weather.com something, right? But what an agent does is calls a weather API and says it will be 12 degree and raining, right? Similarly, if you tell it to email colleague the report, right? So what a plain LLM will do is, here's a draft email. It will do some summarization or reasoning, but it will tell you, here is a draft email. You can copy and send this to John, your colleague maybe, right? So what it is doing is, it will do the reasoning, but it will not perform any task. But what an agent does is, sends the email to somebody and replies send, right? Reply to my unread messages, right? Let's say you give it a task that reply to my unread Slack messages. Here's then what an LLM, given the list of messages, what an LLM will do is, here's what you could say to each person. It will just give you that, hey, tell X person this, tell Y person this, right? Based on the messages you provided. But agent, what it will do is, it will open your inbox or Slack, reads them and sends the replies, right? So we saw the difference between plain LLMs and agents, right? LLMs are, yes, so just to reiterate one more, the example, a plain LLM is, here's how to book a flight, right? Let's say if you give it a question that, hey, book a flight for me. So it will give you the steps. Here's how you can book a flight. It will read data from website, fetch data, and explain you the process to book a website. But what an agent has, it will book the flight on behalf of you and send you a confirmation message that ABC123 is booked for you. So agent is nothing using LLMs to take actions, right? Not only fetch information. And we saw the whole system around agents, what actually is agent, right? So we have a user, and users type in certain query, or they can trigger certain requests via cron job or any other stuff. Then the request goes and sits in onto the server. The server which hosts the LLMs, the user query is sent to the LLM, and the LLM responds back, right? But the server also, apart from just like asking the question to LLM and getting back the response and giving back it to the user, the server has certain tool calls which are associated with it. These tools are the ones which perform actions, right? Which gives the capability to LLM to perform actions. For example, let's say if you say book a flight for me, right? So first this query will come to the server, and the server will forward it to the LLM, right? So the LLM knows that I have certain tools I have certain functions or tools at the server level which are defined, which have the capability to book a flight, search a flight, use any custom user defined function, right? So the LLM will give the back response to the server that, hey, call this function, book a flight with this parameters, and the server will internally make the function call and book the flight and again pass the response back to the LLM. So we had seen it in the last class that the talking between the server and the LLM happens in a loop. The user just gives a goal, and the server and the LLM keeps on talking in a loop until that goal is achieved, or it knows that it no more can do that task. There are some limitations or something, right? So this whole system around it is called agent. So this whole system, the one which is highlighted with dotted lines, is called an agentic system, or this is the agent, right? Agent is not the LLM, but the system around it. And we also saw in the last class that the server can also save the interactions between the server and the LLM in a memory. So that can also be done. So this whole ecosystem is called agents. That is what we had looked in the last class, right? Now let's look at what are the drawbacks of agents, or why multi-agents are required, right? The agent works, but it has three real world weaknesses, right? Adding tools is painful, right? We had seen it in the last class that we have to define the tools, we have to give the definition of the tool, and what did we see? We have to give the definition of the tool, and we have to also give the JSON schema for the tool, which will be passed to the LLM, and which should include the description, the parameters, everything of the tool correctly, right? Then only LLM can take a decision that, hey, server, you can call this tool to get some certain task done, right? So we saw that we have to define the tools, right? It's not magical that the LLM knows all these tools. We define the tool. We as users or the software developers or whatever system we are defining, as per that, we define the rules, right? And we then pass the JSON schema to the description. But why this adding tools is painful, right? Let's say if you every time you want to add a new capability, right, you have to go in and define new tools, right? Let's say 5 more APIs came in over here. So you will have to again go in and add those definition for those tools, the JSON schema, and pass it on to the LLM. So it needs frequent update, right? So this is a painful process, right? And the second drawback with agents is one brain does not scale across domains. Like a single agent juggling fraud detection and customer communication and refunds gets confused, right? So let's say you have a task that, hey, fraud detection is a task, right? Let's say, let's take an example. So first you have to detect the fraud, then you have to communicate to the customer, and then you have to issue a refund. So these are three different tasks, right? Each of the three different tasks might have certain steps associated with it. So if I build a single agent which has to do all of these three things, then it can become confusing for the agent, right? So this is one drawback, and this is one drawback of agents, and why multi-agents is required, right? So like you can imagine it like this. So if I have to build in all the three capabilities into one agent itself, right? I would need a bigger prompt with more unrelated tools. I would have a bigger prompt with more unrelated tools, more chances to pick the wrong one, and higher cost as well, right? So imagine the scenario, like if I am detecting that I'm building that fraud detection system, right? And if I need 40 functions around it, right? So if I have just one single agent per flow, then I'll have to attach all the 40 functions over here, right? So when the LLM is deciding which tool to call, or when an action has to be taken, it can be confusing for the LLM because you have attached so many functions to it, right? Calling the right function might become confusing for the problem. That is why we should not, like if the task is very complex, single agent cannot complete it. And the last point is agents, it forgets, close the chat, and your agent has amnesia, right? It forgets everything. As soon as you close the chat, it forgets all the context, everything, right? So there are three problems we saw, right? Adding tools is painful. One brain cannot scale across domains, which means that one agent cannot solve complex problems. And memory is also a problem. As soon as we close the chat, the agent should not forget all the context, right? So we'll see how these three problems are solved, right? The first one is so the today's agenda is we'll learn about model context protocol, which is solving the first problem. Adding tools is painful, right? So like we saw, adding 40 tools or like adding new tools to my tool set is a painful process. I have to update the code every time, right? So MCP solves this problem, how agents discover and use tools at scale. We look at it. Then multi-agents, right? Instead of having a single agent doing everything, we'll see the concept how multi-agents work, many specialized agents working together. And then we'll also look at memory, right? Remembering within and across conversations, right? Remembering the context which is done within the chat or across conversations, across multiple conversations, right? So what we have seen till now is like these are the pains. Adding tools is painful. Our brain does not, one brain does not scale across domains, and the agents keep on forgetting. They don't have memory. So MCP, multi-agents, and memory is what these three things are the ones which will solve the above three problems, right? So going into the first one, which is model context protocol. So the first problem with tools is tools don't scale, right? We saw that already. Say we want our agent to use Slack, send a message, read a channel, and search past messages, right? So think of a use case or a scenario wherein what you have built an agent where what do you want the agent to do? Basically is to go into your team channel, okay, and then every day send a summary of what was discussed throughout the day, right? At the end of the day, right? So you have built an agent around it, right? So Slack gives you certain APIs, right? To send a message, to read a channel, to read the messages in a channel, send a message to a channel, and search past the different messages in the channel, right? Slack exposes all this functionality as a REST API, right? For every Slack API, our use case needs we handwrite a tool definition and the code to call it, right? So if let's say I'm building that agent, right? So summarization Slack agent, right? So what for these three APIs, which is like sending a message, reading a channel, and then searching for past messages, for all this, these are the APIs provided to me via Slack. So all this, while I'm developing the agent, what will I have to do is I'll have to define all these three tools, right? We saw it in the last class that we'll have to define tools for all of them, right? So I'll define three tools at the server level. Like coming back to this example, I will have to define these three tools at the server level, right? Over here, right? So these three tools will have to be defined by me. and then the agent can call these tools to do certain actions, right? So now you can see the problem, right? Let's say if I need to, tomorrow I need 5 different APIs. Day after I need 5 more different APIs. So every time I need to add a tool, I have to add a tool call. I have to define the tool and do all the processing over here, right? Which needs application update, right? So tools is not a scalable option. That is where MCP comes in, right? I'll just quickly revise like what we saw in the last channel, what we have to do, right? For this particular example, what we had to do is like, let's say if I have to send Slack message, then at a server level, I will first define a function that sends Slack message, and it takes the channel name and text and does some processing, right? Then what I do for tool calling is describe it as a tool, right? Then I'll have to give this tool, this is my tool, right? So we already saw that for this tool, we have to give a name, description, what are the parameters and everything. And then we pass this tool or the schema to the LLM when a user question comes, right, over here. So this is what we had seen. And now see how it is a problem. Like what I was saying is, if I have, so initially when I build the application, 3 APIs were enough. I want to update the capability of my agent. I have to every time follow all these 3 steps: define the tool, then describe the tool, and then for every call to the LLM, I have to basically pass all the tools, right? This is a painful process. It does not scale, right? So how does MCP solve this problem, right? So the drawbacks are obvious. Like I said, TDS to code one tool wrapper per API endpoint, right? It's brittle. Slack ships a new changed API, our code breaks. Developer burden, we define every tool, not the people who own the API. So what this point tells you is, like, see, I am calling Slack APIs, right? But since I am building the application, I have to give a correct description of the Slack API which I want to call when I'm giving the tools definition, right? So this is a developer burden. I might or might not have a correct understanding of the tool, but in order to use it in my agent, I have to give all this, right? This can be a problem because I did not develop the API. So how will I know what's the correct description of the API, right? And we had already seen that when we provide the description, we have to give all this information. What does the tool do, when it should be used, what each parameters mean, what the tool returns, and some examples of it, so that the LLM can pick the right tool at the right time, right? So these all things are a burden. So how does MCP solve this? Instead of wrapping Slack's API, what happens if Slack stands up as an MCP server that exposes its own capabilities as a ready-made tools, right? Now, instead of me going in and defining all these tools over here, what if I have a server which says, hey, I have these capabilities, API 1, API 2, API 3, API 4. You can use these capabilities, and the agent can, what it can do is, now the solution that you have created does not have to define those tools. These tools will be defined automatically by Slack, right? Slack will create its own MCP server, and it will expose that I have these capabilities, which are the tools. Now, what you have to do is, you have to know just the LLM. Now, when you're building the solution, it has to know what capabilities or what APIs are available and what do they do. Now, when a user query comes in, I know what tool sets are available to me, and I can accordingly do the same processing. So the difference between MCP and a normal flow is, like, when a user posts in a query, right? I have a server, and like we saw in the server, we have certain tools, and we have tool 1, tool 2, tool 3. So the person who is developing the application has to define all these things, right? And then the server and the LLM interact between them to do in a loop to take certain actions, right? So what MCP does is, right, it does not changes everything. What it does is, user will pass in the query, but even before taking into the user query, right, what the server will do is, it will connect to a few MCP servers, okay? MCP1, maybe MCP2, MCP3, right? And these MCP server, they define that I have access to tool 1, I have access to tool 2. They will give you that these are the functions. Now, while during this process, you don't define the tools, you just have access to the tools, and the LLM can now interact with these tools, right? So I think it should be clear what is the difference between MCP and tools definition, right? We'll go into more examples, but this is a high level overview that what an MCP server does, right? Just focus on the tools call. Previously, if you are developing an agentic workflow, you have to define the tools, right? MCP server, what it says is, hey, the user or the application developer does not have to define the tools. Instead, if I'm developing a Slack API, a Slack app, maybe Slack can give me a set of tools that it exposes. If Slack defines those tools, maybe they will be more accurate, right? Since they are the owners of it. So, right, that is what MCP server is. MCP servers are basically, in agentic systems, when you want to talk to any third-party systems, instead of defining the tools on your own, you depend on that particular company or product to provide you an MCP server. MCP server is nothing, but it lists all the tools that it has, and then your agent can talk to it, right? We'll look into more details of it. So how does the workflow of an MCP, how does an MCP workflow look like? Like I said, first, let's say the user is there, right? An agent is an MCP client, right? And Slack, let's say Slack has an MCP server, right? We'll take the same example that we are building a Slack agent. So, and we'll see what is the flow diagram or what happens, how does the user workflow happens, right? So I'm building a Slack agent which will do summarization, right? It will look into my team Slack channel, right? Team Slack channel. And then at the end of the day, it will post the summary, right? So I want to build an agentic solution like that. So I build the agent. So now I have built the agent, but how will it happen? And now Slack is providing me some MCP servers, which will basically take care of providing me the APIs. So I am no more defining this tool 1, tool 2, tool 3. Slack has given me all the tools. I just need to register to this Slack MCP server, right? So how will the workflow happen? First, the agent will register itself with the Slack MCP server. It will send a message, connect, what tools you have, right? So what this Slack MCP server will do is it will give it at the tool list, all the tool list, T1, T2, T3, all the tools, whatever it has, it will give that list, right? So this is at the initialization phase. When the agent is initializing or when the Python code is initializing, it will be even before the user query comes in, this happens already before that, right? Now, when a user query comes in, LLM reads the descriptions and picks which tool to call, right? It has already the list of tools which it can call. Now, based on the user query, it will just decide which tool call should happen. So let's say it decides that call send Slack message, right? Send a Slack message, right? So it will tell to the MCP server, hey, call this tool, send Slack message. So the MCP server on behalf of the agent will execute this particular tool or the function and send the result back, right? Result can be status sent, right? Then LLM will reply to the user that done, posted, right? I have posted a summary of this. So you saw, right? So what benefit we got with MCP is like we didn't have to define all the tools. Even before starting any conversation, we just registered with the MCP server of Slack. MCP server of Slack gave me all the tools which I had. Now the LLM just decides, hey, based on the user query, which tool should I call, right? And tells the MCP server to execute that particular tool call or function call and return back the result. When it returns back the result, it processes the result and gives the back answer to the user. This can, in agentic flow, this can happen in loop, right? That's what agent are. They do certain tasks. So that is what is happening over here, right? Now let's take a very simple example. I just want to show you, like, if we have to develop an MCP server, right? How does it actually look like? So let me go to the screen and then maybe go here, new window, or maybe I think MCP example will be fine. So here, what I've done is I have already developed a small MCP application, very, very simple, a server.py, wherein what it does is this is the MCP server, right? So what I'm doing over here is I have defined some of the basic functions like how to add a number, how to multiply a number, greet a user, return current time, then reverse text or server info, something like that. And I'm just starting the function. And since this is an MCP server, I'm just doing MCP.1. We can use fast MCP. This is a Python package which is available to develop MCP servers, right? So this is a simple MCP server that I have developed just to show you the concept of what is MCP, right? And if you see, we are using decorators over here, which is MCP.tool. What it tells is, it just tells that these are the tools available at the MCP server, right? So now in Cursor, you must be already knowing that we can basically register MCP servers, right? And then when you type in anything, the MCP server automatically, the LLM does know that what tools it has access to, and then based on your user query, it will automatically call those tools, right? So I go to this tools and MCP section, and over here, if you see, I have already executed these tools. I have already registered this MCP server. So see, this simple MCP server which I have defined is registered, and then it is also while I register to this step, right? It gives me what capabilities it has: add, multiply, greet, current time, reverse text, server info, and everything, right? So now when I'm building, like, consider this analogy with Slack, right? So when what Slack will do is Slack will write this server.py, or it will create this MCP server and provide me all these functions. Now, since Slack is providing me all these functions and I am not creating myself these tools, I have an advantage, right? Slack is the owner of these functions. So Slack knows a lot about these functions. So it will define them correctly, right? Instead of me going in and defining, right? So this is how I'll create a MCP server And then I'm just taking a simple example of like registering this MCP server over here in my cursor. So basically what it is cursor is an MCP client. So MCP clients talk to MCP server to get some tasks done, right? So so this is an MCP client, and I'm already connected to an MCP server. Now let's say if I give a question, greet Ankit, right? Let's see if it recognizes whether it has to make a tool call or not. See, it's telling I'll check the available MCP server to see if there is a greeting capability. I don't know. It should have already, since the tool, there's a greet tool. Let me read in the schema before calling. So this is all LLM, the agent, right? It is calling. Now it knows that, hey, at the MCP server, there is a greet function already there. And what parameter does it take? Name, right? So it is telling, let me execute this function let me tell the MCP server to execute this function, right? So now it passes the call to the MCP server, and MCP server says, hello, Ankit, welcome to your first MCP server. So basically this is, so MCP servers are also nothing, just servers wherein you define whatever tools you can provide, right? Rather than developers going in who are using, let's say you are a product company, and then basically instead of, if a developer wants to use those APIs of the product in their application, whatever agentic application they have built, rather than they going in and defining tools in their agents, you provide an MCP server with all the functions that you want to provide to the users, right? And they can register to their MCP server and execute the tools, right? And then execute the tools, and where your server itself will basically execute the tools and give back the results to the agents or whatever whatever is trying to call this MCP server. So this is a basic flow that I have taken very simple example. Like we can also take reverse text. For example, let's say if I say, so this is an MCP client, right? So let's say if I say reverse the text A, B, C, D, E, F, right? So let's see if so instead of, see, the major distinction over here is it's not directly going in and doing a reverse directly, right? LLMs can do it directly itself, but it's checking, do I have a tool registered with myself? So it sees that, okay, there is a tool in the tool list where I can forward this task to an MCP server. It is asking, should I forward this task? I run this task. It passes this task to the MCP server. MCP server gives back the response that FEDCBA is the reverse of this, and then it formats and gives me this response. So this is what a basic MCP server looks like, right? I hope this should make it clear what are MCP servers, why were MCP servers required at first place, and what problems they were solving. Now let's deep dive into multi-agents, like what are multi-agents and why are they even required? We already know that a single agent is perfect for a single domain specific task, right? Now let's say if we have a complex task, which may be like flagging an unauthorized payment, or a payment system which detects fraud, right? So if I have to design that system, what I would do is, like, whenever a payment is made, a trigger might happen that should detect whether a fraud has been done or not. So to detect the fraud, there might be some ML rules, some rules engine coming into picture, which might check whether the amount is above, like, let's say 10 lakhs, if the user country is not the current country where the transaction is being made, or it's or if the transaction is at some unusual time, right? So we could have certain rules, right? So detecting fraud is one task. Whenever a payment is being made, detecting fraud is one task that has to be done. Once the user has detected, or once the fraud is detected, what we need to do is we need to take certain actions, right? Let's say if a fraud is detected, right, then we need to freeze the account and do a refund to the user, right? So this is another action based on whether a fraud is there or not. I need to take a certain set of actions. This itself can also be complex. You need to verify the user account, freeze the account, and issue a refund. Then once this is done, I need to also communicate to the user that via email or call that, hey, we detected this thing, or we saw your complaint regarding this thing, and then communicate to the user that we have detected whether a fraud was there or not, and you have taken the appropriate action or not, right? So if you see this whole thing, right, it's a complex task, right? So if I use a single agent to build this whole workflow, there is a problem, right? So what is this problem? Putting all of it into one agent gives you a confused generalist with 40 tools and bloated prompt, right? So fraud detection itself might have certain specific skills, or like 10 to 20 skills which are required, or tool calls required to detect whether it's a fraud or not, right? Taking action might have certain tools registered with it, like let's say 10 tools on how to like freeze account, how to issue a refund. So we'll be defining all those actions over here, right? And then for communication, like drafting an email, maybe a Slack, maybe a WhatsApp message, maybe a normal SMS, right? So there might be different tools calls for this. So different expertise are required for different areas, right, in this complex workflow. So instead of having one agent wherein we make one big workflow, what we do is we use multi-agents in this case, wherein we decompose the task. Like detecting fraud becomes the task for one of the agents. Taking action becomes taking the appropriate action becomes the responsibility of one of the agents. Communicating to the customer becomes the responsibility of one of the agents, right? Something you can think of it like microservices, right? In a microservice, every service has a specific responsibility, right? Instead of building one monolithic system that handles everything. So same concept over here in multi-agent comes in. And the problem why multi-agents is required is like, again, the same thing. You will have, so let's say if you build a single agentic workflow for all of this, right? So let's say you might have 40 different tools and 40 different tools to do specific tasks, right? Now LLMs have specific, specific context window, right? We can only send to, for example, let's say we can only, in one message, we can specify only like, let's say, use 20,000 characters or stuff, right? So if I put in all the, if my application needs 40 tools and I want to provide the context to the LLM of everything, right, in all the messages that I pass, then the context will become very huge, right? Instead, what I should do is I should decompose my application, and maybe for fraud detection, I have agent one, for taking appropriate action, agent two, and for communicating to the user, agent three, right? But we know that, okay, there needs to be some coordination between these three agents, and then how we can accomplish a specific goal, right? So we'll see how can we use a design pattern so that we develop this multi-agentic workflow and then agents communicate with each other. But first, I want to say that for these kinds of use cases, right, we require agents with specific domain expertise. The agents are independent with separate context management and specialized tools for their task, right? Agent one has its own set of tools, own set of tasks, and own context, right? I don't have to give the fraud agent the context of or the tools to send a email, right? I don't need to do that. For taking action, I don't need to provide the agent which takes action. I should not provide the tools or the rules of how to detect the fraud, right? I can split down. Basically, if I take this whole task and break it into multiple agents, right? One thing which I want to call out over here is Anthropic reported that a system of Opus 4 leader plus a few sub-agents, which were like Sonnet 4, like they developed a system wherein there was a leader, which was Opus 4 model, and there were few agents which were using Sonnet 4 model. They outperformed a single Opus 4 agent on deep research tasks. So what they were trying to do is they wanted to do some deep research tasks, and they experimented with two workflows. One is the multi-agent workflow, and one is a single agent workflow. In the multi-agent workflow, they took a leader model, which is Opus 4, and some sub-agents, and they did this deep research. And they took a single agent also, which was Opus 4, and did some deep research analysis, right? So this multi-agent framework, it outperformed the single agent framework. So that is what the power of multi-agents is. But there are certain places we should be really careful. If our only for complex tasks we should use multi-agents. If the task is simple enough, or a single domain is involved, you should use single agents, right? Now let's look at one design pattern which is used across, right? If you are implementing a multi-design, if you are using a multi-agent, basically we need to implement the orchestrator design pattern, right? So what is the orchestrator design pattern? Is like so basically at the center there will be a lead agent, right? That will be the orchestrator. And the orchestrator will first, like let's say when a user query comes in, right? The work of the orchestrator is to plan or break down the task into sub-tasks and then delegate it to sub agents, right? So the flow happens like this. The user query comes in. Now the lead agent plans, right? The lead agent breaks the goal into subtasks and writes the plan to memory. So the user query came in, lead agent created a plan and write down the task or something to some memory. Memory could be anything in memory, or let's say database or Redis, anything, right? Then it delegates. It hands each subtask to a specialized sub agent, right? So the lead agent knows that I have some sub agents which have different capabilities. If I go back to our example, like fraud detection was one capability, right? Then another was taking action, and the other one was like let's say communication, right? So lead agent will break down the task that first I need to detect whether a fraud has happened. then I need to take some action like refund or freeze the user account and start a refund, right? Then I need to communicate to the user. So when a user query comes in, then the lead agent will define like decide or create a plan and then delegate the task to specific agents, right? This can happen in parallel or it can also happen sequentially, right? It depends totally on the use case, right? So now the lead agent delegates the task to the sub agents. The sub agents do their particular specific task and return back the results to the lead agent. Now the lead agent, after getting the response from all the sub agents, it synthesizes or summarizes that the set of actions done by these agents, they were able to solve the goal or solve the problem for the user or not, or the goal for which the user had entered the query, that is met or not, right? So that is the work of the lead agent. So like I said, the lead agent breaks the goal into subtask and verifies and writes the plan to memory. Delegate, it hands each subtask to a specialized sub-agent. Sub-agents, this is important. What they do is they run their own loops, right? We had talked about this in the previous workflow that in when we create agents, basically there is a specific goal of the user and we have a loop going on between the server and the LLM, right, to achieve that task. It's not like a one-shot thing, right? So each sub-agents, they run their own loops, right? Each is a full agent, its own think, react, and observe. Think, act, and observe, right? We saw the react loop, right? That agents run, right? So each sub-agent is a full agent, right? They run its own thinking, acting, observing, right? So when during the fraud detection, what I mean to say is when this sub-agent is required, there is not a single flow that, hey, I will pass this information and the sub-agent can respond me back within one shot, right? Sub-agent will do the analysis. Hey, I need this to, I have a set of steps. And for fraud detection, I want to know this criteria. So it will think, it will act, it will observe. A full loop will go in over here in the sub-agent workflow, right? Then when all the agents have done their work, the work of synthesizing or aggregating the information is what is done at the leader agent, right? Sub agents report results back to the lead agent, and the lead combines them and returns the final result to the user, right? So that will happen in multi-agent workflow, and this is what the orchestrator design pattern is. Now let's take an example, very simple example, wherein we'll try to fit in the orchestrator pattern to our fraud detection workflow, and it will make it completely clear what was I talking about, right? So let's say a user query came in, there's a $2,000 charge. I didn't make it, right? So he sees that in his credit card statement, there's a 2,000, he has been charged for $2,000 and he comes in and complains to the chatbot that I didn't make it, right? So let's say we have built an agentic system which can detect frauds or which can answer or which can identify frauds and take appropriate action. We have developed that agentic system using multi-agents, right? So what will happen when this user query comes in? It will come to the lead agent, right? So the lead agent that we saw is like it will plan, right? So what will it plan? What do I need to do? It will use the React loop and it will come up with a plan that I first need to check if it's a fraud or not, then act on it and tell the customer accordingly, right? So it created this plan. Now it will see my first task is check if it's a fraud or not. So it sees that I have a sub agent which can do fraud detection, right? So I must delegate this task to the fraud agent. So it will pass the query to the fraud agent. The fraud agent checks the transaction history plus risk score and reports back high risk charges where in another country it can likely be a fraud, right? So the leader agent communicated to the fraud agent, hey, detect whether it was a fraud or not. The fraud agent did the analysis and returns back to the leader agent. Now what the leader agent will do is it will see the response from the fraud agent, and now it will take the next. It decides that now I have to call the action agent, right? I have to delegate one task to the action agent, wherein the action agent has to freeze the card and start a refund. So what leader agent sees that, hey, I know that there is a fraud. Now I should call the action agent because the action agent is capable of taking actions if a fraud has occurred. So it will delegate the second task to the, it's happening all sequentially. The lead agent will pass on the task to the action agent. The action agent will then freeze the cards and starts a refund and reports back again to the leader agent that the card is frozen. Refund of 2000 has been initiated and the ETA is 3 days, right? So the action agent again took some action and reported back to the lead agent. So the lead agent now has the context of both the actions that have been done by this agent and this agent. Fraud was detected and I have taken appropriate action. Now, according to its plan, what was it? We should also communicate to the customer. So it knows that I have a comms agent, right? So what it will do is it drafts a clear friend. It now calls the comm agent and tells it that, hey, you need to draft a message to the customer and tell it that whatever steps we have done, we have identified that there was a fraud. and whatever the actions that we have taken. So it gives all the context to the comms agent, and then the comms agent will draft a clear friendly message, and that also reports back to the reports back to the leader agent, customer notified via email or SMS. So sub agent 3, which is the comms agent, will take the action and report it back to the leader agent. Now the leader agent synthesizes everything and replies to the user. We confirm that the charge was fraudulent, froze your card, and started a 2000 refund arriving in 3 days. A confirmation is in your email, right? So see how we decomposed a complex task into multiple agentic workflow, and then we were able to complete this, right? But multi-agent system, it's not as easy as as it looks like. When you go to production, there are certain challenges that you may hit with multi-agent system. You might already be seeing these problems. First one is, like, let's say task delegation. You have to design the leader agent in such a way that it can do effective task delegation, right? If it does not does effective task delegation, the system itself fails, right? Is the lead agent actually good at splitting the work well, right? Then you have to see how isolation versus sharing is happening. So what it means is, like, agents, there are sub agents, right? So there may be scenarios wherein, like, sub agents might need context from other agents, right? And there might be scenarios that where I don't want to pass in all my like all the agents should not get the similar set of instructions, because it might not be relevant to them, right? So information overload also should not happen, right? So you have to design in such a way that isolation, when should I do isolation of information and when should I share the information between the agents, that should be taken care into very that should be taken into account very effectively. So that is one problem. How do you design a system which does that, right? Sub agents need their own context, but sometimes need to share findings. Getting this balance right is hard, right? Lead assessment. Now the leader agent, can the lead correctly judge if a sub agent result is good enough, or does it accept garbage, right? So when the sub agents are returning back results to the lead agent, you have to design the lead agent in such a way that it is able to do an assessment whether the sub agents are returning correct information or not. Otherwise, it can be a problem. I think I don't need to explain much because the problem is very evident. And from a cost perspective, multi-agents are obviously expensive. Anthropic reported that 15x token usage versus a single agent workflow. If you develop a single agent workflow, the tokens are less. If you have a multi-agent workflow, it costs you 15x the token usage, right? Which is very clear. And then debugging, as we can already see by the above points, that debugging will be extremely hard in case of multi-agent systems, because already LLMs are non-deterministic, right? Same prompt, different paths. You can see that same prompt can lead to different paths. So how each system has to be, or each sub agent has to be really good at doing the right thing, right? So if a failure happens, it's very hard to detect that where did the failure happen. I developed the system, but did agent 1 fail, did agent 2 fail, or did agent 3 fail, right? For my task, debugging this will be like really tough in case of multi-agent. So that is also one actual challenge of developing multi-agent systems. But overall, what my take is, like, we should, if the tasks are simple enough, if the task is simple enough, then we should use single agents itself. Most of the time, 90% of the time, we should use single agents. But if it becomes complex, then only we should go into multi-agents and this orchestration workflow. Until and unless single agents cannot solve that problem, we should not try to like create multi-agents workflow, right? Because it comes with its own challenges, which may be very daunting, right? So that was about multi-agents, like why are multi-agents required? And we took a use case and saw like how multi-agents solve a problem, right? And we also looked at its disadvantages. At the end of the class, we'll also see a program wherein, like, I'll show you how actually a multi-agent system, we'll take a real program and do a task using multi-agent and see how it works, right? Before that, let's go into memory, because single agent and multi agents, all of them use memory, right? We know a little bit about memory already. What memory actually is? Memory is the history of agent's decision, what decisions it has taken, what tool calls it has made, results, and the feedback, right? It's also a history of, like, interaction with the user, right? So that is what memory in context of agent means, right? The chat that has happened between the user and the agent, right? The chat that has the reasoning which the agent did to solve a particular task, right? That is also history, right? The tool calls that it made to solve a particular task, that should also be stored in somewhere, right? So that it can look into it, right? So storing all of this requires memory. So that we'll be looking at, like, what things can we use for memory, right? But memory has one trade-off, right? In this case, so let's say one problem with AI systems is like we all know, right? We have heard this that if you want to, you want an LLM to answer very accurately, provide it as much context as you can, right? So the context will obviously be fetched from memory. Like when I'm in a chat application, let's say I want to solve a complex problem, right? But I'm building slowly. Like let's say if I want to find like let's say if I want to find a bug in a code, right, in a big code base. So what will I do? First, I will go into the chat application and I will tell you that, hey, because the LLM right now does not have the context of the code, what I will do is, hey, can you give me the architecture of this feature in the code base, right? So it will get to know about the code base. Then I will say, hey, what this function is doing in this whole context. Then it can give you the context of the function. Then I will say, hey, this is the error I am getting. So now see, it has context of the architecture, the current function, and it can now effectively answer what is the bug, right? So we store the architecture and the functioning of the current function in memory or in the chats in a subsequent chat that we are having, right? So that is memory, right? But the problem with memory is like, I mean, since we provided all the context, the better context we provide, the better answer LLM will give. So there is a trade-off. If you use more memory, you give more context for the current action, and then the LLM gives you better decisions. But there is a drawback also. When you use more memory, it eats the LLM's context window, right? And there are costs and limits repercussion, right? What happens is like when you are using more memory, right? So LLMs have a finite context window, right, of limited tokens. So now I cannot fill in all the history of the user interaction into every time into the context window. There is a limitation, right? So the problem is like that I want correct answers. For that, I want to give all the context to the LLM. But we have to design our systems in such a way that I give it the right context, because there is a limitation on LLM that it can only process certain tokens at a time, right? So memory is not free. It consumes the finite context window, so we manage it. So there are basically two types of memory in context of LLM: short term and long term, right? Short-term memory is limited to a single conversation. So when I'm in a conversation with a chatbot, when I'm in a particular session, right? So short-term memory is limited to a single conversation thread. It is just a list of previous chat messages, right? So for example, if a user posts a message to an agent that, hey, I am Ankit, user then again posts a message to the agent, what is my name? The agent replies, your name is Ankit, right? So this is short-term memory, wherein I am keeping the messages of the user into RAM, or like I am keeping these messages in memory so that when the user asks some personal information, I can respond back to it. So this is short-term memory, wherein like I am having a session with the chatbot and I keep the previous messages, right? So to example this, to just show you this example, what happens is like one more point before it is like LLMs itself are stateless, right? I want to explain this part. This is very important. The LLM itself is stateless. When it responded back, your name is Ankit, right? It did not store any state from this particular message that you had sent, but the surrounding engineering helped it to so that the LLM can answer this. Let's see how this happened is, let's say you are the user, right? So when you sent message one, right, which is my name is Ankit, right, it went to the LLM, right? So the LLM is stateless. It will not store this information that, hey, the current logged in user is Ankit. No, right? LLM will just process or see this request. Now, when you send a message to, right, what do you do? I mean, what as an engineer we do is we pass message one plus message two over here. Okay. So whenever we are sending, like over here, if I have to take an example of any chat application, imagine chat GPT, we are sending a series of messages to the user, not one message, right? So whenever I'm sending messages, what I'm doing is I'm prepending the message. I'm always, when I'm in a current session, I am always prepending the previous messages. Like when I'm sending message three, I will do message one plus message two plus message three. So basically, I'm keeping a history of the messages that the user has sent while and the bot has sent. I'm keeping that history intact to build the right context for the LLM. That, hey, what is going around? What is the user query? How did it started? How did we get to the answer? All the context is preserved, right? So LLM in all those cases, like your first message will go to the LLM, right? So it does not store anything. When the message two goes, right, message one plus message two has went to the LLM. So that is when the LLM can answer your name is Ankit. It's not that LLM had stored any information regarding your user profile. They are stateless. Okay. So I wanted to emphasize this point that LLMs don't have any memory. We build engineering around the LLM so that we provided the right context by maybe keeping the message history or stuff. So short-term memory is nothing. But for a single conversation thread, we keep a list of the previous messages of the chat. That is called short-term memory, right? Now let's look into what long-term memory is, and then I will come back to this problem, which is compaction, right? Long-term memory is reserving context across conversations, right? Long-term memory is available across multiple conversation threads. It stores factual information about a user, name, age, preference, that should outlive any single chat, right? So what it means is, like, let's say if I'm having multiple chat with you in multiple sessions, right? Not in one session. I had a discussion with the chatbot today and then tomorrow and then day after, right? So some information about the user should be stored, right? I should not ask it the LLM again and again, right? So that is long-term memory. So so let's see a scenario where long-term memory will be useful. Let's say I have a scene one wherein I fill in a visa form, right? So what do I do is basically the agent, I want to fill up a visa form. So I tell the agent, please fill this form for your visa application, or the agent tells me, please fill the form for your visa application. User, sure, please share the details needed. Okay, I think this is I think interchangeable. I think a user should be here and the agent should be here. As a user, I will tell, please fill the form for my visa application, and the agent says, sure, please share the details needed. I share my details. My name is Ankit Kaur, my phone number is this, and all the other information that is needed to fill the user form, right? Then the agent says, form filled, download the PDF file, right? Now let's say again I come back a few days later and I have a brand new scenario, no long-term memories, right? Up from this conversation, the user did not or the chatbot did not store any information. Okay, the chatbot did not store any information. Now, so what will happen when I come to again to one of the conversation? What will happen basically is a new conversation starts. I tell the agent, I tell the agent I am hungry. So the agent see, I see, would you like me to suggest restaurants nearby, right? So the user says, yes, please. Agent replies, restaurant 123. User says, book 123 for 8 p.m. Agent, please share your name and contact number so that I can go ahead and do the booking. So obviously you will be frustrated. You'll say, I told you this earlier, right? The agent forgot across threads. So this was my thread wherein I was filling the visa form. I had provided all my information. I wanted the agent to do some other task since it was not using long-term memory. So basically it forgets about the information, right? So the agent did learn the name in scene one, but short-term memory is per thread. Okay. The agent did learn the name in scene one, but short-term memory is per thread. In this thread, if I would have asked the same question or continued this conversation over here, maybe since it had short-term memory, it could have answered that. But since this was another session in another chat, the agent could not remember my information because it was not storing it did not have long-term memory. Okay. So new conversation, it starts blank. That's the gap long-term memory fills, right? So we saw the scenario that we should use some kind of long-term memory. And what is this long-term memory and how do we use it? We'll see that. So if we would have used long-term memory, what would have happened is basically when you tell the LLM that go ahead and book 1, 2, 3 for 8 p.m., it should directly reply because it already knew your name from long-term memory, booked under name Ankit, name pulled from long-term memory, and the user might have been delighted with the experience, right? So this is what is short-term memory and long-term memory. And for long-term memory, you can use any database, right? You can use maybe NoSQL databases like DynamoDB, MongoDB, or anything, whatever to your preference or the structure, how you want to store the messages, database can be used. And primarily short-term memory is kept in memory itself. We don't need any database because we just keep an array of messages or history of messages because it is limited to the current thread itself, not like across threads, right? Now, an interesting question comes is when actually in terms of if I'm using a long term, maybe I'm using I want to use long term memory, right? So when should I write the user information because I'm having a chat with the user, right? I'm in a conversation with the user. How should I design the system that the user preferences or the user data is written into long term memory, right? So there are different patterns like when should the information should be written in memory. Pattern A is end of session batch end of session, like you ended one session with the chatbot, so the conversation ends and in the background, the LLM extracts all the messages and stores some information about the user, that the username, whatever is important, not all the information, that the username is Ankit, prefers 8 p.m. bookings, vegetarian, right? And it stores it into any vector DB, or maybe it can store it in any other DB, no SQL DB, whatever the choice is. Now, that is one way that whenever a conversation ends, you can store the user information, whatever you processed from the chat. Pattern B also could be that during the conversation itself, in line, if you figure out some personalized information about the user, you can store it in the memory at that point itself. After each turn or after a few turns, right? The system decides, is there anything worth saving, and writes immediately, right? This is one more pattern that you can use. And then pattern C is explicit tool triggered, right? What this is about is, this is pretty interesting. The agent has a save memory tool call, right? Which takes in a fact, right? And the LLM decides when to call it, or the user explicitly says, remember that I am allergic, or when the user explicitly says something specific about himself, that remember that I'm allergic to nuts, then what should happen is LLM should has a tool call already associated with it, which is called save memory. LLM decides that, hey, maybe the user is telling me an important information about himself. I should make this tool call, which is save memory and fact, which will go in and save the information about the user, right? So this can also happen. So these are three different these are three different patterns which can be used when you are developing an application and you want to write some user preferences or store some user preferences into database, right? Now, one complementary thing which should happen is, now I have written all the information or stored all the information about the user gradually when the user was interacting with me, right? So when a conversation starts, do we pull everything, right? Now, in my one of the sessions, I provided or collected a lot of information about the user. So whenever a conversation now look at strategies, like when or how should I load those information or the facts about user, right? Strategy one could be load all. Like when you start a chat, if a user has 10 to 20 short facts, you can just inject all of them into the system prompt, right? Like, let's say, I think something got messed up over here. What I could do is, like, when I'm starting the conversation, if I have some small information about the user, that the name of the user is Ankit, the city which he lives in is in Hyderabad. So I should load all this information into the system prompt every time when a user is starting a new message, right? Strategy two could be RAG, right? The real answer for skill. When we are building applications where there are millions of users, we can use a RAG workflow. When memory grows large, hundreds, thousands of facts, plus episodic history, you do semantic retrieval. Embed the memories as vectors, and at the start of each turn, fetch only the top K relevant ones for the current query, right? So what it is saying over here is, like when we are storing, right? We saw over here, we are storing the information of the user, right? So what we do is, every time we store all the information into a vector database or a RAG system, and then whenever I need some information, or the LLM takes that call, that I need some information about the user preference, right? So what it will do is, it will go in and follow the RAG workflow and fetch in like top K relevant results which are relevant to that particular query, and get the preference, right? This is one more this is strategy two. And then strategy three could be tired memory, right? What it means is, MemGPT is one tool which uses which popularized treating memory like a computer's RAM versus disk, right? What it does is, core working memory, always in context, tiny profile. So if a user has a profile, right? So what we do over here is, some small information about the user is always loaded or kept in working memory. And if there are like a lot of facts about the user, then we use archival memory, which is a huge store on the disk, pulled via retrieval tool, calls only when needed, right? When I need specific information, like what it means is, like some basic information about the user, I will keep it in the core working memory or in the RAM, right? And if there are a lot of specific information about the user, then I store it into a database and only pull it when it's required. Okay, so that is what MemGPT does, and this is called tired memory, right? So here, so this was short-term memory and long-term memory, and we also saw that if I'm building an application, when should I write, right? If I'm using long-term memory, when should I write it to the database? Because long-term memory is stored somewhere in database, Redis, wherever. When should I write, and when should I retrieve? It totally depends on your use case, right? So putting all this together, basically the typical production lifecycle looks like this, right? During chat, every turn, right? Embed the user message, right? What we are doing is, when I'm chatting with ChatGPT, when I'm typing in some messages, I embed the user message, which is converted into an embedding. Then, based on that, I retrieve top K relevant long-term memories, right? What it means is, like, let's say if if I am asking about my name or some of my specific user references or some of my information which I have provided you earlier, right? So what this flow is telling is I always store the user information or the user info in vector DB. Okay. Now, whenever user types in a chat, I embed the user message and retrieve the top K preferences, right? If the user is asking, let's say I've given it my meal preference, I've given my flight preference in my earlier messages. So all that information, you store it in the vector DB. Now, whenever a new session comes up, every time when the user starts, let's say if I'm telling you to book a flight and I've already some time down in the past, I've told you about my preference that I like Indigo flights, right? So what you do whenever the user query comes in, I embed it and then I look into the vector DB. There I will see that, hey, the user is talking about flight. And in the vector DB, I already have that information that the user likes Indigo flights. So I will retrieve the top K relevant terms, which is I will get that information of the user preference. And then I always load the small user profile like name and all those things. Small information like name, which is frequently used, I will store it. And preference information, I will fetch it from the DB, from the long-term memory. So I keep a combination of long and short-term memory and then send the user query. So what I will do is user query plus some user info, right? Basics, I will store it in short-term memory because it is used every now and then. Preferences or like which are not used every now and then, I store it in long-term memory. And whenever a user is querying me something, I pull up all this basic plus preferences, small info, not overload or pull it in such a way that the context window is not impacted such along, and then put this information in the user session. Now, whenever a user posts in any query or any message, right, along with this, I'm passing all this information. So now using this information, the LLM can take the right information and it feels that it's very customized, right? So this is how we use this. Right. And then when the session basically ends, basically what I do is maybe I'll have a background job that will summarize the transcription, extract durable facts, dedupe against existing, and assert the store. So in a session, I have loaded some of these user preferences, but in the current session, if I get some more information about the user, I should, after the end of the session, I should have a background job or something which will take the current chat, see if there is some user information that I can store, and just store it in the vector database. So that you can try this. There is a memory mode, and while in ChatGPT there are two modes: remember conversations plus not remember conversations, right? So if you go with remember conversations, what will happen basically is every time you are typing in something or asking a personal question, your profile information is being stored somewhere, so that tomorrow when you ask a similar question, or the company knows about what your preferences are, right? So this is how memory can be used in case of multi-agents or single agents, right? Now let's go into code and let's see how, if I have to implement a multi-agent workflow with memory, how does it look like? Okay, I hope my screen is visible. Let me reconnect. Now here, what we will do is we'll design a small application and we'll use multi-agents over here, right? So this notebook builds a deep research style multi-agent system wherein I want to do some deep research on one of the topics, right? So, and I will use multi-agents to develop an agent, right? So let's say I'm developing an agent which does deep research, right? And uses multi-agents. So we'll use MCP server for tools, one, or like we had seen, right? We'll keep one orchestrator and 3 sub-agents, and then we'll see the use case of short-term memory plus long-term memory, right? So what is the goal of the overall system? On being asked a research question, the orchestrator delegates to specialized sub-agents that pull data from a public MCP server and get back a clean synthesized report, right? So what I'm trying to do over here is, let's say if you want to learn about any specific topic, or if you want an agent to do some deep research and tell you about some topic, right? So I'm developing an agent that you can do how will you develop that agent? I'm developing one such agent, right? Like notebook LLM can be one example, like wherein you go in and type it, I want to learn about React, right? So what this agent will do is, first it will see what is the up-to-date library for React? What is the current version? It will fetch the current version and the docs for the current version, and then it will go to the specific repo, like the GitHub repo for React 17, and maybe if it's publicly available, and then whatever facts are there in the documentation, it will verify via the code. Like if the Git also has the same code, it will, and then an orchestrator will will actually look at the information from these agents and then synthesize the information and give it back to the user, right? So like I said, like we had seen in multiple agents, right? There will be, and whenever we use multiple agents, we have an orchestrator. Orchestrator commands the sub agents and synthesizes information from all of these agents and then returns back to the user. So here we'll be connecting to two MCP server. One is from context 7. What does context 7 do? Basically, context 7 is your go-to for general well-known library documentation. What does context 7 stores? Let me quickly show you context 7. Up-to-date docs for LLMs and AI code editors. Get the latest documentation and code into Cursor, Claude, or other LLMs. So if there are certain popular libraries or stuff, right? So it will contain the docs for all of them, right? And what does Git MCP does is, let's say, like I told, if there is if you want to look at the actual repo of React, right? Let's say if you are doing a deep analysis on React, this will give you the documentation of React, and Git MCP will give you the actual repo of the code of React, right? So since you want to do a deep analysis, you will see, hey, docs say this, and then the code actually says this. Are they correct? Or if a user asks a question related to something, the orchestrator, what will do is it will look at the docs, it will look at the code, and then synthesize the information and answer back to the user, right? So one use case would be technical due diligence researcher for an engineering team choosing a library, right? Let's say you are an engineering team and you are evaluating libraries, whether I should use React or Angular, right? So imagine you are a senior engineer and your team is deciding we should adopt LangGraph or Haystack or roll in it LangChain for a new agentic platform. You are developing a new agentic platform, and your manager has told you to evaluate that LangGraph is good, Haystack is good, or LangChain, the raw LangChain library is good. Normally, what you'll do is read the official docs for each of the project, and then what you will do is clone their repos to see like the code examples actually are, and you will cross check whether the marketing docs, like the docs that React or Angular provided, match what's actually in the repo, right? It's not a fluke or not, or whether those capabilities which are demonstrated in docs are matching the code or not. You will do that, right? And then write a comparison. So we are building an agent which will do this for you, like basically it is evaluating a particular framework or doing a comparison, right? So what we will do is we'll use all the concepts: LangGraph, LangChain, LangChain OpenAI, and LangChain MCP and adapters. First, we'll install all these Python libraries. It's taking some time. Let me quickly in the meantime, let me show you the next block, which is wherein like I am importing some more other libraries like async.io, JSON for formatting the messages, then chat OpenAI so that I can use OpenAI as my model, and then from LangChain, like human message, AI message, so that I can have a distinction. And then like since I want to connect to multiple MCP, multi-server MCP client, I'm using these methods which are provided out of the box from LangChain, right? So let me execute this. So basically these two are the setup which is required. And we have already talked about that LangChain and LangGraph are used for agentic development so that you don't have to write everything out of the box. They are libraries which are present so that they make your work easier, so that you don't have to hard code or you don't have to write everything from scratch. Now let's connect to the MCP servers like we had seen. So both of these context 7 and Git MCP provide their MCP servers, right? So we'll just connect to them. MCP, so multi-server MCP client, which we saw over here, right? What it does is a LangChain adapter for one or more MCP server tools. Communication happens via STDIO, SSE, server sentiments, or streamable HTTP, right? When a new tool is added to any of these MCP servers, the clients are notified, right? A specific notification is already sent so that it can be utilized correctly, right? So what we'll do is we'll give, so when you register an so I am creating an MCP client wherein I want to connect to these MCP servers, right? And see what tools, get tools, so what tools these MCP servers provide, right? So I connected to these MCP servers, and you can see these are the tools provided by these two MCP servers, right? Which is resolve library ID, query docs, match common library owner, repo mapping, search generic documents, search generic code. Like all of this is provided by these MCP servers. Now let's just do a basic testing. Let's try to call, see, we saw here, right? Fetch generic documentation. So what I want to do is, let's see if this is working correctly or not. So I had all the tools present in here, all the tools, right? So what I will do is I will loop over the tools and I will see if the tool name is fetch generic documentation. I will tell it to fetch information about LangGraph and LangChain AI, where the owner is LangChain AI, right? So I'm making this tool call to fetch some information. Okay, let's execute it. And this particular tool is available in Git MCP. So you can see over here for my query, right? I wanted generic documentation, right? So it provided LangGraph documentation has moved to this thing, but it's telling this introduction to LangGraph, a library for building stateful multi-factor applications with LLM. Okay. So it's giving you this information that LangGraph, where the owner is LangChain AI, what is the generic documentation available? So it's telling this repo has might be being moved to some other place. Okay. So that might be the case, but if I give some other query, it will work out. But let's go into the examples further. It will become more clear. So over here, let's see separately what context 7 tools offers and what Git MCP tools are available to us. Okay. So that we can specifically know that context 7 tools provide us resolve library ID and query docs, right? What it means is like React is a library. So if I want to get the library ID, I can get that. And if I want to query the docs, this is one tool available in context 7 MCP server. So I can call these tools, right? Whereas Git MCP tool provides these tools, which is search generic code, search generic documentation, fetch generic URL content, right? Since it's related to code, you can see you can search within a specific repo. Like I said, right, context 7 is like it has a context of all the libraries. What my agent does is first it will try to read the docs of a particular repo like React, and then pull its code also, so that if the user has any questions regarding it, it can answer from code also, right? So now let's build the sub agent, right? We had seen that we will use the agentic workflow. So we'll have two types of agent. One is library agent, one is the GitHub agent, and the third one is synthesizer. So library agent will pull the information related to the library. GitHub agent will pull the code for the information provided by the library agent. Like let's say if I want to learn about LangGraph. So LangGraph documentation will be pulled by library agent. The code will be pulled by GitHub agent, and whatever capabilities are then like they will run a loop within themselves and give the information, and then the synthesizer will synthesize this information and return back to the user. So what we are doing is what LLM model we want to use. Since I have the keys available for GPT-4o mini, I want to use this LLM with temperature set to 0. And then I'm just creating the agents, right? So here you can see I'm creating a library agent. Important thing to note over here is in the library agent, right? I'm just providing the tools which are related to context 7 tools. Okay. And then I'm providing a prompt. You are a library documentation specialization specialist. Given a question about a software library framework or package, use the context 7 tools to find the official documentation and answer. Workflow call resolve workflow. What is the workflow? Call resolve library ID first to find the canonical library ID, then call get library docs with the ID and a focus topic, right? So it's first telling that get the library ID, whatever is the canonical library ID, then use this tool, get library docs with the ID, so that you can get specific doc information. If I would have created a single agent, right, I would have to pass this context 7 tools and Git MCP tools, both of the tools to them, right? Since we have decomposed like a microservice for this library agent, I am just giving context 7 tools, and for this MCP for the GitHub agent, see when I'm creating agent and I'm only passing in the tools the Git MCP tools, right? And the system prompt is you are a GitHub repository specialist. Given a question about a specific open source project, use the Git MCP tools to inspect that project's wiki and answer. Use ask question with the repo owner name and your question. If the question is about repo structure, use this thing, right? So it will fetch the particular repo and then specific information. And then we have a synthesizer agent also. What it does, what it says is you are a research synthesizer. You will be given a research question and a set of findings gathered, right, by other agents. In our case, it's this library agent and GitHub agent. And your job is to write a clear, well-structured final report that directly answers the question using those findings, right? Cite which sub-agent provided which fact. If the findings are insufficient, say so. explicitly do not fabricate, right? So that it does not hallucinate. So over here right now with this create agent function, I'm just creating these three agents. Let me click on create, execute. So this executed. Now we have seen, right, what will happen is we saw that in multi-agents, we use the orchestrator design pattern. So the orchestrator reads the conversation so far, the user question, whatever sub-agents have reported, decide who should work next, right? We saw this, right? Whether the library agent should work, the GitHub agent should work, synthesizer should work, or when all of them has provided their information, should it finish or not, right? And what this does is it just gives you a command that the orchestrator, what it will do is it will just give a command that, hey, go to this particular agent. Okay, we'll look at this. By looking at the code, it will become more clear. So first and foremost, we have a router, right? This is a pydantic model, which basically means is like it will just tell that what is the next agent to be called and what is the reasoning behind calling this particular agent, right? So this is one thing. And then this is the orchestrator prompt, wherein I give the orchestrator the instructions that you are the orchestrator of a deep research team with 3 workers. I give it library agent, users context 7, GitHub agent, synthesizer agent. You will receive a research question and the running transcripts of what each worker has produced so far. Your job each turn, pick exactly one of this and explain why in one sentence. Routing rules, a question about how to use a library, its API or its feature, library agent. We give it some examples, right? So here also same thing like function definition. We are giving what tools it has access to, which agents does it have access to, and what rules should it follow, or some examples we are giving over here, right? So we are just defining the orchestrator over here, right? If you see, this is just the definition. Okay, so see, we have this LLM with structured output wherein we pass the router and we are just passing all the messages, right? Whatever messages it has, and then it will give you the next agent to call, right? And if in the go to, right, it will decide which agent to first. It will take a decision. We take the decision, and from the decision, whenever I pass it to the orchestrator, okay. So this part is doing like a message comes to the orchestrator. Orchestrator decides which agent to call next. And then if the go to is finished, that means in the loop, I have already all the agents have done their research and I want to go to finish. So I'll just say end, right? So how this whole, if I have to summarize how this whole, what all this thing is about is first user question lands in a state messages, orchestrator runs, LLM reads the prompt plus full transcript, returns router, right? Based on the user message, it decides it has to call library agent, right? So it will give you the command, go to library agent, right? LangGraph, now what will LangGraph come into picture? It jumps to the library agent. It does it works, appends findings to the messages, then hands back the controller to the orchestrator. So look over here. First, we define the orchestrator. The user message came in. The orchestrator will it will analyze the user message and it will issue a command, go to library agent. So the control will pass to the library agent. And then the library agent will do the analysis. It will have all the set of messages from the orchestrator and it will do some processing and it will append the messages, whatever analysis it has done, and pass back to the control to the orchestrator. So that is what we are using over here. And we are using LangGraph over here. So these are some, this maybe you can consider as root node, and these are some sub nodes. They are doing analysis and passing it over to the root node, right? So like we saw, LangGraph jumps to library agent, it does it work, appends findings to the message, then hands back control to the orchestrator. Orchestrator runs again. Now it can see the library findings, returns command, go to GitHub agent. Now orchestrator is the decision maker. It got the, for my particular query, it got that, hey, I got the official docs for it. I want to also consult the GitHub agent, right? Where I want to pull the code. So it will pass on the control to GitHub agent. Now GitHub agent will work, do its analysis and give it back to the orchestrator. This is how it will work all together, right? So we use both LangChain and LangGraph over here. LangChain gives you the LLM capability with structured output, right? And LangGraph gives you the shared state, the command, go to navigation, and the loop that keeps calling the orchestrator until end, right? Together, they turn a plain chatbot into a controllable looping manager that delegates work, right? Wrapping now in this, we are building that graph workflow that we spoke about. We are building the worker nodes. So we are building the graph and we are adding the nodes. Orchestrator, see, we are telling orchestrator, this is the orchestrator, right? We are specifying that this is the orchestrator node. Okay, we created an orchestrator and we are specifying this is the orchestrator node. And these are like make worker node are created using the library agent, GitHub, and the synthesizer agent, right? So we are basically creating the nodes, right? And then we build the graph, right? So here, let's do that. Okay, I think I didn't execute this. Let me execute this. Let me execute this. Now see, I have this set of queries. right? How does LangGraph implement multi-agent supervision and what does it do? I want to know the official LangGraph documentation say about using it with MCP tools. Then click the most popular then check the most popular GitHub repo that uses multi-graphs, which is not LangChain, and note what they say. Then check the official GitHub repo from LangChain and note what they say. Give me a report from all the three sources at the end, highlighting the difference between official docs and unofficial docs. So this is my workflow. My workflow itself, I have right now, just to give you guys an example, I have written it in such a way that all the agents are called, right? So first it will use the library agent to pull the docs of LangGraph. Then it will go to the Git MCP agent to fetch the code. And then it will go to the synthesizer agent as well, right? And then what I'm doing is the above graph that I had initialized over here, right? This state graph. Now I'm just in the initial state. I'm passing my user query. Context is the user query. This is the human message, and this is just saying that this is the human message. And then I'm invoking using the initial state, right? I'm invoking the graph using the initial state. So if I do that, the whole multi-agent system starts working. Okay. So the first call will go to the orchestrator. The orchestrator will create a plan, whatever we read, right? It will create a plan, what it should do for this particular user query. It will identify that, okay, first I should call the library agent. Then it will pass on the control to the library agent. See, it's printing all of this. The library agent will return back the results. Then it will see if it needs more information, it will call the GitHub agent. Then again, the control will be passed back to the orchestrator or any other thing, whatever is required. And this is the whole flow is dynamic, right? It's not that we have hard coded anything based on the user query. It's just doing some analysis. The loop is going on and it's analyzing the work done by previous agents and giving me back the results. One thing which I want to call out is, see, I have given a recursion limit over here is 25, which is like after 25 turns, if you're not able to figure out the answer, maybe quit. Because let's say for vague queries, let's say if the agent goes into infinite loop, it can cost us tokens. So that is why we need to give the correct recursion limit and everything, right? So here you can see the trace it has given. This was the human message, whatever you wanted. It called the library agent first. From that, it got the documentation. Then it called the GitHub agent. There it got the code. It verified the documentation, and then so on and so forth. Then it passed the information to synthesizer, and this is its final answer. Okay. So this is how multi-agents work, right? Now let's look at one last thing, which is basically memory. Like we had seen short-term memory and long-term memory. So if we want to just use short-term memory, I'll just take an example of short-term memory that I'm developing in a chat application, and I want to keep a short-term memory. So in so how we can use the LangGraph to do short-term memory is, we'll just use this memory saver module, wherein we'll just provide that graph with memory, right? And it will, in the current chat, it will preserve the context. Okay, so let's say my turn one question was, what does context 7 do based on the upstash context 7 GitHub repo, right? So I pass the same question to the orchestrator again over here, right? So graph with memory invoke, right? I'm just calling this. Previously I had done just graph invoke. Now I have initialized graph with memory invoke. So I'm calling this, and this was my human message. What does context 7 do based on upstash context GitHub repo, right? So now the agents are reasoning and figuring out the right answer. Let's wait for it. But while it figures this out, in turn two, what I will do is now tell me how that compares to the LangGraph GitHub repo, right? See how it will preserve the context. First, I asked it, what does context 7 do based on upstash context 7 GitHub repo? So I'm asking what does context 7 do? And now in the second question, I am asking, like, tell me how that compares to LangGraph GitHub repo, right? So if I would have not used memory, it would not know that what is the user asking me to compare against, right? It would have asked you that question or given you that response, right? So because we are using memory, it preserves the context. Okay. So here, see, it gave us this final answer over here. This was our message. Then it did some analysis and reasoning using the agents. And the final answer is this. See, orchestrator gave a finish, so it stopped after this. In between, there were multiple, like it called GitHub agent multiple times. It called synthesizer when GitHub agent and other agents had completed their work. And final answer is based on the findings from the abstracts. Get this, Context 7 is a tool designed to integrate up-to-date version-specific library documentation into AI coding assistants. Its primary purpose is to find accurate current information, which helps developers avoid outdated code, right? So it could infer this answer. Now let's execute this turn 2, where I'm telling it to compare now it with LangGraph GitHub repo, right? Let's see what it gives. Okay, let's wait. We can see the orchestrator was being called. The human message was passed, and then the orchestrator called the GitHub agent. Here also it called the GitHub agent. So there's a reasoning going on, the React loop that we talked about. It did the reasoning and then passed it to the synthesizer agent. It gives us total messages in the thread after 2 turns. For final answer, the report is comparison of LangGraph and Llama index GitHub repository. Okay, I don't know, maybe it went a little wrong over here. It compared LangGraph and Llama index. Uh, while it should have compared context 7 and this thing. I don't know. Let's try one more time to see. LLM responses are non-deterministic, so I'm just trying my luck. But basically, you understand the concept, right? So turn 2 should, since we are in the same chat, it should run. It should like remember the information from here, right? Okay, I'm still not getting it. Maybe, yeah. But I hope the idea is clear. We'll try to debug it further and update it so that you get the right answer. But I think the idea is clear. We looked, today was a lot. We looked into MCP server. Why was it required in the first place? What are multi-agents? How do we use the orchestrator plan for multi-agents, and how memory comes into picture? What is short-term memory and what is long-term memory? Thank you guys for joining in. I'll fix this problem and share the code with you. Maybe something small I'm missing. I don't want to go into debugging it right now, but I'll share the updated code with you guys. Thank you guys for joining in.